Welcome to today's presentation, which is Advances in LPC or Large Particle Count Monitoring in CMP Slurries. As I put this talk together, I decided to add a subtitle of Statistics or a Bear because as I started going through the presentation showing the data, a lot of what we're doing in this field is kind of driven by the statistics because not only is it important in terms of the data we generate, but also in terms of how we generate the systems that we're going to use. We're going to start by looking at why large particle counts are important. And the reason is because the large particle counts affect the yield, the defects, and usually we're talking about scratches on the surface. In this first study that I'm showing, it's showing here on this plot, this is large particle counts, particles per ml larger than, I think this is actually at about 0.6 microns or so on the x-axis, and scratch count on the y-axis. There was a very linear relationship here where the correlation coefficient of about 95% as you look at the relationship between large particle counts and scratch counts. As long as there was an increase of about this concentration, almost 2 times 10 to the 5th particles per gram, then there was a very direct linear relationship between the large particle counts and the scratches. This large particle count was collected using our AccuSizer 780. This was using the LE400 sensor, and later in the talk today I will be describing the different sensors and why we've improved that technology along the way. This is an image from this particular paper, the reference is given here, and this is a scratch on the wafer surface, just kind of showing how it shows up, and that's what creates these defects. And in this one circle here you see this is some agglomerated particles, and these are the kind of things that create the scratches. In the next study, what we're seeing again, and this data is collected by the AccuSizer, this time with the FX sensor, and here we're looking at data from Ceria CMP slurries. And here the difference was in the creation of the CMP slurries, the effective calcination time on the large particle count as you see here. So there was a 4 and a 6 hour calcination time for these two different slurries. And as we see for the 6 hour calcinated time slurry, there's much fewer particle counts than in the 4 hour. And what was surprising is actually there was a smaller crystalline size for the 4 hour calcination time slurry, but these smaller crystalline sizes then aggregated much easier and created the higher large particle count. What we see down here are scratch counts on the wafer, and these scratch counts were collected using a 10-core surface scan. And what we see is at the higher large particle count, a much higher scratch count. And conversely, where there was a lower large particle count, much fewer scratches. We'll look at two more studies here. In the upper one, this is a very direct correlation. Here we're talking about the number of large particles, and we're using larger than 5 microns for the large particle count here. And we're looking at concentration of large particle counts versus counts again on the wafer, probably from like a 10-core surface scan. And what we see is a direct correlation. As there's a higher particle count, there's a higher wafer count. And this is what leads to scratches and reductions in yield. In the study we see down below, what we're looking at is defect density, and what we're looking at defect density as a function of time, and what was happening here is we went from not filtering the CMP slurry to using a 0.7 micron filter to using a 0.5 micron filter. And as we're using finer filtration, as we're reducing the large particle counts, we're seeing fewer scratches on the wafer surfaces. So I think actually the relationship between LPC, scratch count, and yield is pretty well proven and is accepted in the industry. Now let's talk about the instruments we need to use to track the LPCs. Now we certainly do still sell lab systems. You see a picture here of the AccuSizer APS. And some people use these lab instruments to check the slurries as they come into the fab area, and that's a good starting point. But really, the concerns happen down here where we're working with the polishing tools, and most of the interest we have now is in our point-of-use systems. And part of that is because large particle counts actually are created in the process. And since they're created in the process and affected by the process, we want to take the measurements in the process. And lots of customers said, hey, what I'd like to have just a system where I don't have to do any dilution. I don't want to deal with any of this messy stuff of dilution. And we do have systems where we measure without dilution, but I'm going to talk about the statistics of coincidence and talk about there are times where we do need to dilute these samples in order to have very accurate LPCs. And then we're also going to talk about, if we're going to find these large particle counts, just the statistics required to find them in a very reproducible manner. So in the ideal world, all we'd have to do is put some filters in the process, right? And all these particles would just disappear. But that isn't really the way the real world works. So certainly there are filters usually in the delivery line and also point of use, but there still are particles downstream of filters. And how do we know when to change these filters? That's one of the uses of online particle counting, is rather than just changing the filters just because it's Friday morning, let's actually track the particle count, and that's what we see here, particle count as a function of time. And let's replace the filters based on when we actually see the increase in large particle count. By using an online system here, we're not only reducing the number of scratches on the wafer, but we're also optimizing our use of the filter, and since these filters aren't free, it also optimizes our use of the filters and the expense of them. I'd mentioned that we can create large particle counts in the process, and part of that is just from pumping the slurry. And this could be for reasons such as shear stress. What we see in the upper graph is these different colored lines are particle concentration values at different sizes. This top line is the larger sizes, particles larger than 1 micron. And what we just see as a function of time as we're recirculating the CMP slurry, we're seeing this increase in LPCs, and we'd want to track that online, and we would want to know when we need to take corrective actions when that reaches too high of a level. What we see down here in the lower graph is this is data shared from a customer, and what we see here, again, the different color lines are different sizes, and the top line is the largest particle size. As we're tracking the particles continuously using a point of view system, we reach some kind of an upset condition here. And as we saw the increase in the particle counts, there was a corollary increase in the number of scratches on the surface. So we want to be measuring these online also to find these upset conditions, because when this occurs, we might want to take corrective actions so that we're not processing wafers knowing that we're going to have reduced yield during that period. This slide also shows the effect not just of pumping, but what goes on as we pump the slurry. So what we see in the upper graph is we take a tote, and what we're doing is we're pumping along, and as we reach near the bottom, we might see an increase in the number of particles. So we're wanting to monitor the pumping of the slurry from the tote or from the supply tank. And as we reach the very bottom, if we see this increase in particle counts as we reach the bottom, we might want to take corrective actions. The reason there might be additional particles in the bottom, even though these are very small particles, there could be some sedimentation. And as we're pumping from the bottom, that's when we're going to have troubles with large particle counts. What we see in the lower graph is data. This is just particles larger than 1 micron. And what we're seeing is as a function of time, the slurry pumped from the day tank. And as we switch over the tote, we see this large increase. And we might want to take corrective actions and know that we should actually recirculate the sample from a new tote before we start sending it out to the tools where we're working with the CMP process. Here's another graph where we're looking at, this is particle count as a function of time at different sizes. And this is just a study where a tool manufacturer was looking at the effect of a peristaltic pump inside the tool. And just as we recirculate the slurry using this peristaltic pump, this is when we're actually seeing the increase as a function of time. And this could be used to either optimize the use of the peristaltic pump or know what other corrective actions have to be taken in order to reduce the LPCs. So now that we've talked about why LPCs are important, let's start looking at the measurement that is required. As I talked about dilution versus non-dilution, let's talk about why this is important. This is an image of our LE400 sensor. There's a light source. There are 2 detectors. One looks at the extinction, the blockage of light from the presence of particles, and the other one looks at the scattering. As we get to smaller sizes, we get more of a contribution from the scattering. We take these 2 pulses, sum them, bring that into the counter, which is a pulse height analyzer, and then through the use of the calibration curve, we can take each individual particle and convert it to its equivalent particle size. Since this is a one-at-a-time technique, it's a very high-resolution technique, and that's why it's so successful in finding a few large particles, which is what this is all about. Now, we can only have 1 particle at a time in the sensing zone. You see the dimensions of this sensing zone here. So if we have 1 particle at a time, then we have a very accurate representation of the size and concentration. But if you look at the right where we have these 2 particles in the sensing zone at the same time, we're going to size these 2 particles as 1 larger particle, and we have a coincidence error. Because of this, we can only have a certain concentration of particles per ml passing through the system, and for the LE400 sensor, that concentration is 10,000 particles per ml. This sensor works from 0.5 to 400 microns. And as we wanted to work at higher concentrations, we actually looked at what would we need to improve in the sensor technology. And an important advancement in the sensor technology is when we switch from using a collimated light source to a focused laser beam. And when we focus the laser beam, since we're reducing the inspection zone, then we can actually work at much higher concentrations. The FX sensor, which measures from about 0.7 to 20 microns, can work now up on the range of 1 million particles per mil, or a 10 to the third improvement per ml. So by being able to work at higher concentrations, this means with some slurries we don't have to dilute, or we do less dilution for other slurries. Another advantage of focusing the laser beam is, since we are increasing the light intensity, we can also now measure down to a smaller particle size. So with the FX nanosensor, we can now measure down to 0.15 microns and work at this very high concentration, up near 1 million particles per ml. So the sensor technology has advanced considerably to allow us to work at higher concentrations and down to smaller particle sizes. Even though we can work at higher concentrations, we still always have to check for coincidence errors. This is data taken from looking at, this was a Ceria CMP Slurry. And what I was doing with this particular study, I was taking 3 different concentrations of measurements. And this is particle counts here per ml versus size. And if you look at the particle count, this is at 3 different concentrations. And if you look at the 5 micron size point, there is perfect overlay. And this is indication there's no coincidence error here at 5 microns. But if we look down here at 1 micron, as we see the changes in the particle count with concentration, that's saying we are experiencing a coincidence error here. And therefore we would want to work at this lowest concentration. This is where we are outside of the area where we have any coincidence count. And by the way, look at the number of particle size in these studies. This is 704,000 particles. And we'll talk later why we need to measure so many particles to get very accurate, good results. In this slide, I'm showing kind of some changes in the fluidics of the systems. In the far left, this is the point of view system several years ago, and this is designed with no dilution. And certainly we can do measurements on many slurries without dilution. But then here in the center, and then I blow up this particular portion of the fluidics on the right here, we see a great increase in the complexity of the fluidics, and this is in order to be able to do this automatic dilution, and not only to do the dilution, but to do it in such a way that we're gentle with the slurry so that we can still have a very accurate representation of these large particles. And also we need to keep our sensor very clean and flushed in order to make sure that we have very continuous stable results for months on end in point of view situations. So you can see great advancements in the fluidics here, and a lot of what goes on here kind of goes on behind the scenes. There's a lot of control in the software I'll show you, but also in firmware just in terms of flushing this vessel, flushing the sensor. Here you see a filter used to make sure that the diluent we're using is very clean. So this is the advances in the fluidics to improve the performance of our point of view systems, which we call the AccuSizer Mini. This diagram shows how we do a 2-stage dilution in order to take concentrated CMP slurries and dilute it down to the optimum concentration range. So the sample comes into this loop here, and we can vary this loop volume between 1 to 5 ml typically. We bring this into the first dilution chamber. So it's diluted here, and then as we then go from the dilution chamber down to the sensor, we can introduce another continuous line of clean dilute DI water. So we have 2 stages of dilution, stage 1, stage 2, and we control these very carefully to make sure that we eliminate any chance for coincidence errors. And what we'll typically do for any new CMP slurry we haven't seen before, we first work in the lab, understand the optimum conditions for diluting the sample down to the proper range, and then set up the firmware and the software to take those measurements. And this is showing the screens in the software once we understand a new slurry, what kind of settings we need to use to control the system to be at the proper concentration range and the proper measurement time to generate the best data for the measurement. Some things I'll point out here is operation mode. For instance, we can do not only online measurements, but we could bring in a sample bottle to test the system. And we can do that to test the calibration or just to make sure everything is working right with the system. And over here I might point out many ways where we control the flush time of the vessel, the flush time of the sensor. So there's a lot of controls here that we can set up once for any given slurry, and then we can control the system so that we're generating the best possible data for any given slurry. Now let's talk about the statistics of the measurement. I pointed out in a previous slide how I'd collected hundreds of thousands of particles. Why is that? Well, as we think about these results, we always have to think about the error involved with the results. And if we just think of the most simple form of looking at errors is the standard error. And the standard error is the standard deviation divided by the number of particles counted. So we can solve for n, and if we want to deal with a distribution of particles where the standard deviation is 2 microns, and if we can live with a 2% standard error, then we'd need to count 10,000 particles to reach this level of error. So think of this number as 10,000 as a bare minimum before we could really start talking about generating good data in these situations. There was a very rigorous theoretical approach for the number of particles that need to be measured for a given sample of particles in an ISO standard published about 8 years ago. This is the ISO 13322 standard, which is for image analysis. And the way to read this is the standard deviation of the distribution. You know, if all the particles are one size, you can measure one particle and you'd be done with the measurement. But as we have a broader distribution of particles, we need to measure more particles in order to reach a certain confidence level. And in this particular plot, we see this is the geometric standard deviation, if it's 1.6, in order to just calculate the mean value based on the volume basis, would need to count 60,000 particles. And 60,000 particles, think of that as probably a realistic number of at least before we can start getting a good value for the mean. But remember, what we're trying to do with these measurements is find these outliers, the LPCs. So actually we should be looking at many more counts to be able to accurately and repeatably find these outlier particles, the large particle counts that we're looking for. Personally, I'm more of an experimentalist than a theorist. So what I did to understand this better is I took a sample, and in this sample what I did is I measured it, measuring just 400 particles, and then I started increasing how many particles I looked at up to about 40,000. What I'm plotting is D10, D50, and D90. So remember, 90% of the particles are below the D90, 50% are below the D50, and 10% of the particles are below the D10. I plot here the D10, the D50, and the D90 versus the number of particles counted. And what you see is it's fairly stable, but then once I reach this inflection point, which is probably at around 15,000 particles or so, I started finding that the D90 was increasing. And the reason for that is if you just count a few particles, you're just really going to get the central points of the distribution correct. But you really need to look at tens of thousands of particles to start creating a very accurate D90 value. What we're looking at for is these large outlier particles way over here. And this is why I keep stressing the importance of statistics, because if we just count here even 20,000 particles, we're really not going to accurately, consistently find the large particle count over here. So the number I really want us to be thinking about is really to collect hundreds of thousands of particles to be able to consistently have very real, repeatable grasp of the large particle count in the slurry. So now let's start looking at some data we have collected using our systems for some CMP slurries. Here what we did is we took a silica CMP slurry and we spiked it with 1 micron polystyrene latex particles. And what we wanted to do is check the sensitivity to be able to find these large particle counts in a silica CMP slurry. Since we controlled this in the laboratory, we actually knew that we were injecting on the order of 100,000 particles per ml, here right at about 1 micron. And as you look at the concentration before and after the spike, you'll see roughly 100,000 particles per ml spike increase right here at 1 micron, proving how accurate the AccuSizer is in finding these large particle counts. Also notice to do this, we're counting 200,000 to 300,000 particles. And this is the range of counts we like to be in to make certain we're always going to catch any large particle counts. In this study, we took 2 different Ceria CMP slurries. A CMP slurry B had a higher large particle count than CMP slurry A. And what we show here is where we just spiked Ceria A with 1% of the Ceria B, and we see a very repeatable increase in the large particle counts. And then as we increased, and then in the lower graph here, when we spiked it with 10%, we see a very large increase. So what we're proving here is we can consistently find these large particle counts. And I want to point out here we're counting on the order of millions of particles. To really do this consistently, we want to count hundreds of thousands to 1 million particles. And there's really no issue here because we can still do this just in a couple of minutes. Since we can work at higher concentrations, we can actually generate this kind of data where we're collecting hundreds of thousands to millions of particles being inspected in measurements that take just a few minutes. And that's why our AccuSizer system is the best system available to find these few large particles, is partly because of the sensor technology, but also because of the fluidics and us being able to dilute so that we can consistently measure these large particles at very high count rates and never worry about coincidence and have very accurate results. So these are the kind of things we've had to invest in the system so that these systems can then help you increase your yields in the fab. Most of the systems we're installing now are point of use monitors, because the LPCs are created in the fabs in the process sometimes, and that's where we have the most troubles. So we sometimes have customers now who'll buy 40 of these at a shot, install these throughout the fab, and this is a way they're improving their yields to improve their profits by reducing scratches on the surfaces and improving the yields of their semiconductors. There are samples where we don't have to dilute, but when we do, we can dilute in very accurately, very precisely. Give us your CMP slurry, we'll monitor it in the lab, we'll understand what is required, the best way to dilute it, the best way to do the measurements, and build the system so they can work continuously in the lab, in the fab, at the right concentration ranges. Remember, we really want to be measuring at least tens of thousands, preferably hundreds of thousands, to always have the statistics to know where we're always going to find those large particle counts. Because you really can't beat statistics. And as much as when we see the billboards where there's mega millions at $640 million to be won, I have bad news for you. Buying a few tickets, you're not going to win that jackpot. Statistics just don't work that way. And the same thing is true with finding LPCs and CMP slurries. If you think you can just measure a couple hundred particles and find these LPCs, you might get lucky once, you might find some kind of giant upset, but you're not going to be finding what's really going on in the system. You cannot beat the statistics. Therefore, we really need to be looking at these range of number of particles that need to be measured in order to find them consistently.